Okay, so now I want to look at this problem. The only difference is that I'm giving you u of x. U of x, or what this function is, u of xb is equal to 3 sine 5 pi over ax plus 22 sine 19 pi over ax. And let's try to figure out how we can solve this. So what's going to happen when I take this solution and plug in b? On the left-hand side, I'm just going to get this, 3 sine 5 pi over a plus, x, plus 22 sine 19 pi over a x is equal to this, where I plug in y is equal to b. So this will be the sum, k equals 1 to infinity, ak e to the k pi over a b minus e to the minus k pi over a b times sine of k pi over ax. Okay, so now what's going to happen here? The only way these two things can be equal is if the corresponding coefficients are equal. Because what I have on the left-hand side is a sum of these sine functions, and what I have on the right-hand side, or depending on, I guess, from, well, I don't know where your perspective is. On this side, I have a sum of sine functions. On this side, I have a sum of sine functions. And just like two polynomials, or similar to how if I have two polynomials and they're equal to each other, or a polynomial in a Taylor series, which is more like what we have here, and they're equal to each other, the only way that can happen is if the corresponding coefficients are equal to each other. So in other words, this tells me that 3 has to equal ak times e to the k pi over ab minus e to the minus k pi over ab. And it tells me that, where k is equal to 5. And it tells me that 22 is equal to a19 times e to the 19 pi over a b minus e to the minus 19 pi over a b. Okay, and so what this tells me then, the solution is u of xy. Now I know what my ak's are. I can now solve both of these for ak's. So I'm just going to have two terms. For all other values of k, ak is equal to 0 because that's what we have up here. If I look at the k equals 4 term, I don't have a k equals 4 term over here. In other words, the coefficient is 0, and so the coefficient over here has to be 0 as well. In other words, a4 is equal to 0. Or really, a4 times this is equal to 0, but this is not equal to 0, so therefore a4 is equal to 0. Okay, so this is going to be equal to 3. So I've run out of room here. It's going to be equal to 3. Okay, so now I am going to use hyperbolic sign notation just to make things work out. Well, no, because, okay. So this is e to the 5 pi b over a minus e to the minus 5 pi b over a times, I will just put the other exponentials in the denominator, the numerator though. So this is e to the 5 pi y over b minus e to the minus 5 pi y over b sine 5 pi over 8x, and then plus 22, so a19 is going to be 22. Okay, I'm going to multiply by e to the 22 pi y over a minus e to the minus 22 pi y over a. divided by e. Oh man, sorry, this is a 19. E to the 19 pi b over a minus e to the minus 19 pi b over a, all times sine of 19 pi over over a x. Okay, sorry. Let me see if I can zoom in this way, the old-fashioned way of just putting the camera closer. Okay, so that's what we have there. That's what we have there. Okay. So now let's look at a slightly more general situation. Okay, the more general situation is going to be, what if I just am given something like this, the sum k equals 1 to m bk sine k pi over ax. Okay, now what can I do? How do I change this? Okay, well, what's going to change is that now on the left side up here, we're going to have, when I plug in y is equal to b, we're going to have the sum k equals 1 to m bk sine k pi over ax is equal to this. Okay, well, if these two things are equal to each other, again, the only way these two things can be equal to each other is if bk is equal to this for all values of k. So in other words, ak, which is what I really care about, ak, in terms of the solution, ak is what I really care about, ak is equal to bk divided by this part right here, for k going from 1 to m, and then ak is equal to 0 for k bigger than m, because bk is equal to 0 when k is bigger than m. So then this gives us u of xy is equal to the sum k equals 1 to m. Okay, now my ak is going to be equal to bk divided by this. So we'll have bk. Remember, the bk's we're thinking about as being given. They're given up here. So this is bk times e to the k pi y over a minus e to the minus k pi y over a. We're going to divide by this. So this is e to the k pi y over b minus e to the minus k pi y over b. And I'll move out of the way in just a second, times sine of k pi over ax. Okay, so that's the solution for given these bk's. Now, what if instead of a finite sum, we have an infinite sum? So instead of a linear combination here, we have a series, which, just because it sounds good, I like to call infinite linear combination, but some people don't like that. So we're going to go up here to positive infinity. Okay, and this is the solution. Okay, but the problem is we are often not given, we're very rarely given the function, the boundary data this way. Instead, what we're given is some f of x. This is typically what we're given. But by the discussions we've seen so far and the theory that we'll sort of pin down next week, we know that we can write f of x, any reasonable f of x, as an infinite sum like this, for some reasonable meaning of what this equality means. So typically we're given f of x, like we're given a formula for f of x squared, x, 5x minus 17, tangent x, something like that. We're given this, and we want to go up to this point here. Because if we can get to this point here, then we win, because this is the formula. Okay, so now the question is, if I have f of x, how can I figure out what the bk's are? And this is where the orthogonality comes in. And so what I'm going to do is I have f of x, and I know that I can write this as a sum k equals 1 to to infinity bk sine of k pi over ax. Okay, and what I'm going to do is I'm going to use this orthogonality property. I'm going to multiply this by sine of L pi over ax. Do the same thing over here. If I do it on one side, I have to do it on the other side. So this is sine L pi over ax. And then I'm going to integrate from 0 to a. So this is going to be the integral from 0 to a dx. Over here, I'm also going to integrate. I could put the integral there, but it's the integration is linear, so I'm going to put it right here. So and then I'm going to put the integral right here and compress. So this becomes bk times the integral from 0 to a. I don't know how much of what you just saw, how much of what I just said you saw, since I'm standing right here, but I'll get out of the way, and you'll see all of the relevant things. This is what we have. Okay, now what's going to happen here? This integral, so the penultimate thing here, this integral is equal, so this is where the orthogonality comes in. This integral is equal to 0 if L does not equal to k, and it's equal to a over 2 if L is equal to k. So the only non-zero term here is when we have L is equal to k, in which case we get BL times a over 2. And now if I multiply everything by 2 over a, this is just intermediate, we don't really care about that, we have BL is equal to 2 over a. Okay, and so now our general formula, the bk that we write here, is going to be this integral. So except, so my index, my variable here, like I have an L here, so I have a formula for BL here, but my index up here is bk. And so this right here, I'm going to do some somewhat bad notation. I'm going to change this to a k. Now these are disconnected, and what I'm saying is that's what bk is equal to. And that's what we've seen in previous videos, and other videos as well. This is just sort of a fuller picture of what's going on. Okay, so that's it for this video. In the next video, we're going to look at solving Laplace's equation on a rectangle where we have more than one non-zero boundary.